Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now third lecture for week number 9 for our term. In today's lecture, we will be talking about the noise communication. So let me quickly summarize what we have previously discussed about noise. So noise refers to the random and unpredictable electrical signals that are naturally uh, produced within or sometimes external to the system. So the important thing is that we cannot eliminate noise by any mean. In fact, for all communication systems, they have noise at the output at the receiver side to some extent. If the noise variations are very high, in that case the signal can be totally obliterated. Otherwise, it will be corrupted by noise, which may cause problems in the detection of the signal. However, the most common parameter that we use to analyze noise is signal to noise ratio, SNR, because the signal power in comparison to the noise power is actually important for us. So we want to have SNR as high as possible. For most communication system, the most common noise phenomena is thermal noise, which is actually produced by the random motion of charged particle within the conducting media. In most cases, of course, that charged particle is electron. So that electrons, they are always present in those in the media, conducting media, which comprises which makes the communication system. So eventually that thermal noise would always be there no matter what type of system we use. The naturally produced thermal noise, it is actually modeled by a Gaussian distribution with zero mean. So the noise has a standard statistics. Is basically a random signal, as we previously discussed the topic of random processes. So the mathematical model that we use is is Gaussian noise with zero mean, and as I have previously mentioned as well, that the power of the noise is equal to the variance of that noise voltage, the random voltage that we get at the noise system. We also know that there are other parameters related to random signals. So autocorrelation and power spectral density of noise, they are modeled by this formula, where K is Boltzmann constant, theta represents the temperature, G is conductance of the resistance, whatever media you are using. This model for autocorrelation function and power spectral density is plotted in this graph here. Actually, this dotted line is actually the distribution of thermal noise. You see that this here, this here. This graph is plotted with respect to the frequency in gigahertz. You can see that for reasonably high frequencies, the thermal noise amplitude is almost constant. Even for higher frequencies, for this region, the change is very small. So for significantly large part of the spectrum, we see that the power spectral density of the noise voltage is very much constant, close to constant, although it's not exactly constant, but it's close to constant. And you should realize that these are the commonly used band. Normally all the communication systems that we use in real life, they focus on the frequencies which are below these frequencies. For example, the mobile communication, which is made in megahertz, the microwave, which is in initial part of gigahertz. Similarly, satellite systems, they are also focusing on gigahertz, and so on. You can see that the most of the communication systems, these this power they focus on this frequency band. So eventually we can say that for most communication system, the noise power spectral density that we encounter that can be approximately treated as constant. So for simplicity or for mathematical tractability, generally we take the noise voltage to be constant for entire spectrum from 0 to infinity. So this is actually our mathematical assumption, that the noise voltage sorry, not voltage, the power spectral density is constant for all the entire range of the frequencies starting from 0 to infinity. This type of noise is named as white noise. This is referred to as white noise. The autocorrelation function of white noise is given by this impulse function n0 by 2 delta t. This is an impulse function which is also plotted in the graph that I showed here. This thick line is actually the white noise modeled by an impulse function. The thick line here, the constant thick line given by this constant amplitude n0 by 2 is actually representation of white power spectral density of white noise. You can compare this representation with this dotted line. You can see that the white noise is reasonably good model to represent the thermal noise in most of the scenarios. So we can conveniently approximate our thermal noise with this white noise model. Because this autocorrelation function is represented by an impulse function, therefore we always say that the two different samples of noise, they are uncorrelated with each other. So therefore whenever we take measurements of noise, so all the noise samples that we collect, they are independent to each other. There is another important concept related to the noise, because if you see in this white noise model here, you can see that the power spectral density is taken as constant, and if we integrate for entire frequency range from 0 to infinity, so this constant amplitude, constant PSD to infinite band, of course, gives you infinite power. Practically it is not possible, and practically we do not encounter this white noise. Why? Although we use white noise in our normal systems, in modeling of our systems, but you should notice that whenever a signal passes through any system, so system made some changes in that output. So this output actually is dependent on the system and the impulse response of the system. We have previously talked about this, that the output is actually given as the convolution of input and this impulse response. However, here we are talking about the power spectral density. So this is the relationship regarding the power spectral density. The input power spectral density and output power spectral density, they are related by this simple relationship, that output power spectral density is equal to product of input power spectral density multiplied by magnitude of the transfer function. So you can see that this whatever output you get is also dependent on the transfer function. So if we input noise to any system, even if it's white noise, you can see that if white noise is input to the system, the output is actually dependent on the system response as well. So because most systems, they incorporate filters in some extent, for example low pass or band pass filter, so whatever output we get, that will be limited to certain band. So if we apply a white noise to the system, you would see that the output noise will actually be limited to a finite band rather than an infinite band. So output noise is actually limited to that finite band, and eventually it has a finite amount of power, which is represented by its variance. This type of output noise is generally named as filtered noise or band limited noise. So practically we actually work on filtered or band limited noise. We actually do not encounter infinite power from the noise. So let us try to take a simple problem. A white noise is having one-sided PSD. So one-sided PSD, for simplicity, I have taken this PSD to be N naught. So one-sided PSD is given as N naught. You should notice that the two-sided PSD is generally written as N naught by 2, whereas the one-sided PSD is written as N naught. Is passed through a low-pass filter whose transfer function is given like this: hf is equal to 2 e raised to r minus jf. The resulting is passed through a low pass filter whose cutoff frequency is b. So the cutoff frequency is given as b, and we want to find the noise power. So what is the noise power? So we are given the input power spectral density, which is actually n naught. So if I ask you to find the output power spectral density, we know that we have this simple relationship. So hf square, if we calculate the magnitude of this function, 2 e raised to r minus jf. So 2 squared is 4, and magnitude of e raised to r minus jf is actually 1. E raised to r j theta always gives result equal to 1, because from Euler's identity, e raised to r j theta is equal to cos theta plus j sin theta. So if you calculate the magnitude, that will give unit answer. So this is actually related to only phase, does not contain any. So the amplitude for this is actually 1. So the magnitude of h of f square is actually 4. So if we calculate the white noise, which so it will be written as n naught into 4 here. So this is the power spectral density for the signal, and if I ask you to calculate the power, so what is the power, resulting output power? So power will be this PSD multiplied by S naught multiplied by the bandwidth, which is equal to 4 times N naught B. So the power is a finite number, which is 4 times N naught into B, which will come out from this filter. We take another problem. So let's say we have two-sided power spectral density, which is given by N naught by 2, is passed through a low pass filter whose cutoff frequency is W. So what will be the power at the output? So you can see that this is the white noise, which has actually infinite spectrum. It is passes through a low pass filter whose cutoff frequency is given as W. If this white noise passes through this filter, you would see that the output power will be limited to the specific band, which is from minus W to plus W. However, the amplitude will be same as the noise PSD, N naught by 2. So it will have the amplitude to be N naught by 2. And if we want to find the power, we can simply integrate this S naught F, or in other words, we can simply find the area under this curve. So if you find the area, you would see that the noise power spectral density comes out to be Wn naught. Another important concept related to this situation is that of noise equivalent bandwidth. As I have previously mentioned, that for noise, this the output power spectral density is actually dependent on the filter that we incorporate in the system. So typically these filters, they do not have this ideal response, rather they have some practical response. So for all the practical cases, the noise power is actually represented by this relationship N naught by 2, which is the power spectral density of white noise, multiplied by the integral of this hf square, which is filtered square. So, or because of the symmetry, we can simply integrate it from 0 to infinity and multiply it by 2, so giving us this answer that N naught, the noise power will be N naught into integral of this f square df. You can see that the noise power is dependent on two things. One is the N naught, which is the noise power spectral density. Second, this is the integral of hf square. This integral of HF square is actually defined as the noise equivalent bandwidth. Sometimes we call it noise bandwidth. What is noise bandwidth? Which is given by this relationship where this 1 upon G is actually represents the maximum value of this HF squared. So HF square. So basically this is the normalized version of this function here. So therefore the noise power is given by this N will be equal to G into N naught into Bn, which is the noise equivalent bandwidth. Practically, what is the noise equivalent bandwidth? Actually, as I mentioned that the filters have some transfer function that has certain decay. Actually, what we do, we replace that transfer function with a rectangular filter, so that filter response is represented by a rectangular filter, and we make the condition that whatever noise is present in the system, that is confined to that rectangular filter. So the same based on the same noise consideration, whatever bandwidth we get is named as the noise equivalent bandwidth. Say for example, these are two illustrations, one for band pass filter and another for low pass filter. So you can see that this curve is actually the actual response of the filter. This actual response contains some amount of power. So whatever power is there in this actual filter, we collect that power and represent this filter by a rectangular shaped filter like this. So whatever bandwidth is required by that rectangular shaped filter, this is named as the noise equivalent bandwidth. So in order to maintain same power, that means whatever power is in this band of rectangular filter is equal to the amount of power which resides outside that filter. Similar situation is there for the low pass filter. You see that there is a transition band here, the slight transition band. So what we do, we remove that transition band and represent it by a rectangular filter illustrated here, and whatever bandwidth for that rectangular filter is required, that bandwidth is named as the noise equivalent bandwidth for that filter. So noise equivalent bandwidth actually is used in the calculation of noise because it facilitates us to represent the filter by any arbitrary filter by a rectangular filter, which makes our calculation easier and more mathematically tractable. So let us now discuss another perspective. What happens if a signal passes through a noisy channel? So let's say we talk about a baseband transmission with additive noise. So a signal is passing through a baseband system and noise is added to the system. Baseband means there is no modulation included in that baseband system. Typically there are some baseband systems as well, but we generally use these baseband systems for making a comparison with the modulation system that makes a calculation that provides a basis for comparison. The transmission system is LTI system, as we have previously discussed, and noise is additive noise. Practically, the noise in any system can exist in any part of the system. So it exists. It can exist in transmitter components. It can exist in channel. It can exist in receiver component. So noise can exist in any part of the system. However, in our models, we only associate noise at the place where the signal is received. So the noise is substituted at the point where we have the receiver input, because that is the most critical point where the signal strength is at the minimum. So the noise effect is more prominent at that particular point. So that's why for analysis purposes we generally input the noise at that particular point in order to get the worst case scenario incorporated in our calculation. So this is the illustration. So we have some received signal which is to be received at a linear receiver. As I mentioned, although the noise is added to at all the stages in the system, but we add this noise at the place where the signal is input to the receiver. So we have added a noise, and it has a certain power spectral density which is given by G and F. So of course, whatever output you would get, that would be contaminated by this noise. So eventually output would contain two components. One is the signal component, which is represented by XD, and another is the noise component, which is represented by ND. And we know that the noise have an additive effect, so we have represented that the noise is added to the system. So the output would be represented as XD plus Y. If I ask you to find the overall power at the output, so we can, in order to calculate the power, we need to calculate the mean square value. So we take the square of this function and we get the average. So that means we have to calculate the expected value of square of this function XD plus ND whole squared. So of course, if we expand it by the whole square formula, you would see that comes out to be x square d plus 2xd nd plus n square d. And we have previously discussed that the noise is generally uncorrelated with the signal, so we can operate this expectation separately on these functions. And because of the uncorrelation, this xd and nd, the expectation can be separate out for both of them. E of xd and E of nd can be calculated separately. So second thing, this is actually expected value of the noise, which is the mean value of the noise. And as I have previously mentioned that the noise has zero mean, so because of zero mean, I can substitute it to be 0. So this term will become 0. So we will end up with these two terms, E of x square and E of n square d. So I can say that the mean square value of the output is actually mean square value of the input plus the mean square value of the noise. In other words, the output power is equal to the signal power plus noise power. And as I have previously mentioned that the most important parameter that we use to analyze signals is signal to noise ratio. So the signal to noise ratio at the destination would be given by this signal power x square d mean value divided by a mean value of n square t. In case the white noise is input to the system GNF, which is given by eta by 2. So if we have this value as power spectral density of white noise, so the noise power would be represented by this noise equivalent bandwidth multiplied by power spectral density multiplied by the gain G, power gain of the receiver, which will be available at that particular point. So you can see that when the noise is input to the system, a baseband system, that means the noise would have some effect on the signals. Eventually it will generate some signal to noise ratio at the destination side. So let us now consider a simple analog baseband transmission system represented by this diagram here. We have transmitted a signal xt which has a certain amount of power, which is x. Generally we have to incorporate an amplifier at the transmitter, so it has a gain gt. So the transmitted power is st. So at this stage you can see that the source power can be simply represented by the mean square value of the signal x square. So sx is actually x square, whereas the transmitted power would be represented by the gain times this source power, which is gt into sx, or is gt into x square bar. So this is actually the transmitted power that will be transmitted from the system. So this is the transmitter side. The transmitted signal is passes through a channel. We are assuming a distortionless channel. So basically this channel does not cause any distortion. Mathematically, being distortionless channel is represented by this condition, because when a signal passes through any channel, it can have some propagation delay, because it takes a finite amount of time for signal to reach at the receiver side. So the delay is represented as Td, and also there is some attenuation in the signal which is represented by k. So multiplying the transmitted signal xt by this a constant number k and causing some delay does not represent any type of distortion. So this is the mathematical representation of the distortionless channel, that the transmitted signal is received at the receiver exactly in its original form, with some delay and some constant multiple or constant attenuation or gain. Secondly, as we have previously discussed as well, we are working on a finite bandwidth. So our signal, whatever we are transmitting, it's a band limited signal. Therefore it does not have any power spectral density beyond bandwidth. So it has a finite amount of bandwidth. So when the signal passes through a distortionless channel, we know that there is an attenuation that occurs during propagation. So this distortionless channel causes some loss, which is represented by L. So after the channel, the signal is received at the receiver side. So the received signal will be represented by this R, and that will have certain amount of power which is represented by SR. If you try to relate SR with ST, you can see that this is a simple relationship, because there is a loss here L. So the transmitted power would encounter this loss L to give the received signal SR. So this received power SR can be represented as transmitted power divided by the loss encountered by the channel. Of course, this received power can be represented as the mean square value of the received signal as well. So this is the received signal, as we have previously discussed, that we and for our models we add this white noise at this stage when the signal is received at the receiver. So this is the input side of the receiver. So we have added a white noise here, and that white noise is represented by a constant power spectral density, which is given as n0 by 2. After that, the signal is input to the receiver, which is actually represented by two important components. First is the gain or amplifier at the receiver, and second is the low pass filter. So eventually, as I previously mentioned, that after adding noise and passing through the receiver at the destination side, you would be getting two parts of the signal. One is dependent on the signal xdt, and second is the noise component t. So the power at the output side is actually comprised of two powers. One is the signal power, second is the noise power. If we discuss both powers separately, you can see that this signal power is actually related to this SR directly, because the SR relates to the received signal power at the receiver side, which passes through this gain GR to give the power at the destination side as D. So I can say that this signal power at the destination is actually equal to the received power multiplied by this receiver gain GR. So this is actually SR GR, and you can see that from this previous relationship, SR, ST and SX relationship, we can easily relate this received signal power with the transmitted signal power as well. So first thing is the received signal power, which is SD. We can easily calculate this received signal power. Second part is the noise power given by ND. As we know that this noise power is actually related to this white noise, and if we represent the receiver by its equivalent noise bandwidth, in that case the power would be represented by this GR eta Bn, where eta represents, eta is actually same as N naught. Eta is noise power spectral density. We use two notations for power spectral density. So this noise power ND can be represented by the product of the receiver gain and the power spectral density and noise equivalent bandwidth. So for the receiver we have used the bandwidth to be equal to W. Therefore if we want to find the SNR at the destination side, you can see that we have to divide the signal power with the noise power. So the signal power is given by GR SR, and the noise power is given by GR eta Bn. You can see that this GR will go off, and eventually you will get that the noise, so signal to noise ratio would be given as received signal power divided by this eta into W. You can see that there is an important component in the receiver filter, which is a low pass filter, which is generally incorporated in all received filters. Firstly, it actually limits the noise power in the system because it eliminates all the noise which is out of the band which we are working on. Secondly, for the demodulation purposes, if you refer to the demodulation, we also know that we have to recover the original signal through low pass filtering. So in most cases this filtering is needed for modulation as well. So filter is an important part. Second important thing is this receiver gain. You can see that there is an amplifier used in the receiver because generally this SR is very small, and it sometimes it becomes harder to detect. So it is very important to amplify this received power so that we get a significant amount of power at the destination side. However, you should note that this GR at the receiver side, it does not affect the overall signal to noise ratio. Although we are providing some amplification, but this amplification is provided to the received signal as well as to the noise. In both cases its amplification is provided. So this amplification does not affect signal to noise ratio. You can see here when we calculated the signal to noise ratio, the effect of GR is actually cancelled out. So SNR at the destination does not depend on the power amplification in the receiver that we have previously discussed. Typically the signal to noise ratio at the receiver side is represented in decibels. So this table actually summarizes typical examples for different analog transmission systems and the related signal to noise ratio that are used. So if we are working on 5 to 10 SNR, 5 to 10 dB of SNR, so this type of signals actually very hard to detect. They are not detectable. The telephone quality speech is generally designed to have SNR value of 25 to 35 dB. The AM broadcast is actually requires around 40 to 50 dB of SNR at the receiver side. The hi-fi audio generally requires 55 to 65 SNR dB of SNR at the receiver side. The TV video, it requires around 45 to 55 decibels of SNR at the receiver side. So you can see that for the systems, the noise gets added to the system, and eventually it causes some degradation in the system, which is generally measured in terms of its ratio. Although we have at this stage we have only talked about the baseband transmission system. However, the similar type of analysis can be performed for the band pass or modulation based transmission systems as well. So we conclude our discussion at this stage, inshallah. Thank you all.